We're going to start here, chapter 1, which is chemistry in our lives. And as I mentioned, we're going to maybe skip through some of the parts of it a little bit along the way. So when we talk about chemistry, chemistry really does sort of enter into all aspects of life. Um, Obviously, forensic science, for example, uses a lot of chemistry. But chemistry is, every day. There's like food chemists, chemists for like things like shampoo, medicine, tests that we take, so chemistry really does sort of enter into a lot of just regular everyday life. Uh, and what is chemistry? Well, chemistry really is sort of, in most cases, the study of matter. And matter is really anything that sort of occupies space and has mass. So it's pretty much everything. It's a study of the composition, structure, and properties of matter. And when we talk about matter, a lot of what we look at is how matter changes, how matter goes from, say, one state to the next. We also, a lot of times, will look at sort of the energy component, for example, what's happening along the way. So, really, a lot of chemistry involves matter. And when we talk about matter, a lot of times we're talking about sort of the three states of matter. For example, we have the solid state of matter. And in the solid state of matter, things are usually packed in there pretty tight to one another. So that's why when we think about things that are solid, they're really hard, they're rigid, they're hard to break. And that's because pretty much everybody, in most cases, are pretty much just packed in tight to one another. There's also liquid, which is the next sort of state of matter. And in the liquid state of matter, we still have things relatively packed in there pretty tight to each other, atoms, molecules, whatever they may be. The difference is they actually do possess a little bit more energy. And what that allows them to do is they could kind of move past each other because they have a little bit more energy rather than in the solid state where they don't really have a lot of energy. They're just kind of locked in there. They're like, I don't want to move. I don't have enough energy to move. I'm just going to hang out here. In the liquid state, they do have a little bit more energy, so they're able to sort of move past each other. And that's why when you think about a liquid, it's fluid, right? It moves because they have a little bit more energy. The molecules can move around each other. And that's what makes something like a liquid more fluid than, say, a solid, where they're just kind of all clumped together, not really moving all that much. Then we get to gas, which is the last sort of state of matter. And in the gas phase, everybody has completely broken apart from one another. They're flying around. They have probably the most energy of all three states because you need a lot of energy to escape each other, and you also need a lot of energy to continuously fly around. As they're flying around, as we'll talk about when we get to the gas chapter, as they fly around, there's collisions that occur. And as these collisions occur, that's what we associate pressure with, is all those collisions. The more collisions we have, the higher the pressure we have for a gas, the less collisions that we have, the lower the pressure is. So a lot of what we deal with in chemistry deals with these states of matter, things in their solid state, liquid state, gas state, things as they change from, say, solid to liquid, liquid to gas. And there is a change of state that occurs. So as something goes from solid to liquid, that's the process of, what is that called? I take an ice cube out, it starts to melt. Yeah, that's melting, right? You feel bad about your melted ice cube. You got some liquid water at that point. You take the ice cube, you throw it back into the freezer, and it goes through freezing, right? As you go from liquid back to solid. You're making a little pasta for dinner. You put some water up there. You start to boil it, right? And it goes from liquid to gas through a process known as evaporation or vaporization. And if you take gas and bring it back to the liquid state, which you see a lot, probably when you take like a shower and you look at the mirror, there's a lot of water on the mirror, right? That is what is known as condensation. There is also a process, as you may be familiar with, that you could go from the solid state all the way to the gas state and you skip the liquid mess, and that is what is known as sublimation. If you've ever seen dry ice or used dry ice, which is carbon dioxide, if you use dry ice, you should be careful because it's really cold. But it goes from the solid state directly into the gas state, no liquid cleanup in between. So when they send you something that's refrigerated, they usually throw dry ice in there because when it kind of goes from solid to gas, you get no liquid that ruins your whatever they ship to you. Can we go the opposite way, which is gas skipping liquid to solid? The answer is I'm assuming so because I wrote an arrow. So that means that we probably could do that. And that's actually what is known as deposition, like you're depositing something on something. Maybe you're old enough to remember CDs, DVDs. Do they still sell those things? Maybe they do, I think. And that's how they get them shiny. They actually go through a process of deposition and they deposit metals on them, which makes them really, really shiny that you look at. So a lot of times we look at these transitions of states or changes of states, what's happening in chemistry as we go through this. By the way, when I do melting and freezing, for example, does that happen at the same temperature or different temperatures? It actually happens at the same temperature is when that happens. That is the normal melting point or freezing point of a substance. For example, for water, that is 0 degrees Celsius where that happens, 0 degrees Celsius. And it's exactly at 0 degrees Celsius, for example, when that happens in the case of water, that you actually have both phases happening at the same time. So if you're at exactly 0 degrees, you'll have a little bit of liquid water. You have a little bit of ice happening, kind of like ice crystals happening exactly at 0 degrees. It's actually not until you get a little bit above 0 degrees that you fully sort of transition into liquid water. And it's not until you get a little bit below 0 degrees that you actually fully transition into ice. So it really depends what you're doing at that temperature as to which way you're going in terms of energy and heat. Same thing over here when we talk about evaporation and vaporization and condensation also happens at the same temperature. And that's the normal boiling point of a substance. That's the normal boiling point of a substance. And again, that is melting point. And obviously that is freezing point. So a really big aspect of what we look at in chemistry as we're talking about these things happening and these changes of state is the energy component. And when we talk about energy that's happening as we go through these different processes, as we go, for example, from solid to liquid to gas, do I need to put energy in to do that, or do I have to take energy out to do that? Energy has to go in. So energy is absorbed in this case. So if you think about the case of your ice cube, when you take your ice cube out of the freezer and you just put it on the countertop, right? Heat flows from cold to hot or hot to cold. It does go from hot to cold. So when you take your ice cube out and put it on the countertop, the air is hotter than the ice cube. So all the heat from the air goes into the ice cube, which is why it starts to melt. Also, your ice cream, same situation, right? It happens in that situation. So it continues to melt. And if you take that liquid water, as I mentioned a second ago, and you want to cook something like pasta, you put it up on the stove, you put a fire under it, right? So you're adding more energy and heat to it, and it will start to boil. And what happens when it boils is that is basically liquid water turning into gas water, or steam, it's referred to. And those are the bubbles that you see inside those bubbles as it's bubbling, as it's boiling. That's actually steam inside the bubbles. They don't make it to the top sometimes because the pressure outside is greater than the pressure inside on your bubbles, and they pop before they get there, which is why it takes a little while for it to actually boil, right? They gain up enough pressure inside those bubbles to actually make it to the surface before they pop, and then it's actually boiling at that point. So when we talk about energy and absorbing energy in chemistry, those are all processes which are referred to as being endothermic. So endothermic basically means heat and energy is being absorbed. Opposite is true if we started at gas and went to liquid and then went to solid, all of those processes require energy to be released. So if you think about gas molecules that are flying around, moving around, banging into each other, and all these things, as they release their energy, they're going to start flying around a lot slower, right? So they're not going to be flying around as fast, which means when they come in contact with other gas molecules, they no longer have enough energy to fully bounce off each other and escape. What ends up happening is they kind of clump and like fall into the liquid phase, basically. And if you continue to take energy out, they will lose more energy and no longer be fluid, and they will lock into place in terms of solid. So going in that direction, that is the energy is being released. That in chemistry is what is known as being exothermic type process, is when heat and energy is released. Going back to our ice cube example, why does liquid water freeze when you put it into the freezer? It is because when you take the liquid water, the water now is at a higher temperature, right, than the freezer air. So when you put that water into the freezer, heat is going to transfer from the hotter water out. That's going to require the water now to freeze, right? Slow up, don't have any more energy. And that is what happens when you put liquid water in there to like make ice cubes or something like that. It is going to lose energy again, because in that situation, liquid water is actually hotter than the air there in the freezer. Any questions on that there? So again, chemistry deals with a lot of these things, what happens at melting points, freezing points, boiling points, transitions, and energy is a really big component. I think chapter 3 is energy, that we'll talk about these sort of processes again. When we talk about chemicals, again, like I said, we're going to kind of skip through some of this stuff. We'll talk a little bit about scientific method, which I think is good. When we talk about the scientific method, it really starts with an observation. And that is really sort of where a lot of scientific discovery sort of begins with, which is, you observe something or somebody observes something happening. And the idea is like, wow, that was kind of interesting. We just observed something happening. So a lot of sort of discovery comes with people trying to figure out, maybe why that happens. So you have some type of observation, and usually that will lead you to a hypothesis. And a hypothesis, a good hypothesis, is sort of a testable sort of explanation of what you observed. So a lot of times in chemistry or in science, we like to have hypotheses where we could then go to the laboratory and test it and try to figure out, what's going on through some type of experimentation, to try to discover what's happening. And that obviously leads to the next part of it, which again are experiments where we're trying to sort of test our hypothesis. Most of the time when you do this in sort of a chemistry lab or just a science lab in general, when you go do those experiments, maybe you get lucky and you actually see what happened and what your hypothesis was. But most of the time what ends up happening is, we kind of circle back and you maybe observe something new or something else had happened. And if you're working for somebody like an academic lab or something like that, you go tell them, hey, I saw this happen when I did this experiment. It's gonna go, cool, that's exciting. Go do some more experiments and see what happens. And that leads to maybe your hypothesis being revised, a new hypothesis, some more testing, some more observations, and more testing. The hopeful result of all this is at some point, some type of conclusion will basically come out of this. And that could usually be in the form of one of two things, either a theory, usually, or a law. So hopefully the end result of all this sort of experimentation, observations, hypothesis is either you get a theory or a law. And there is sort of a difference between a theory and a law. So you could kind of think of a theory like this. A theory is sort of a tentative explanation of what you're observing. It is believed to be what is happening and the reasons why something is happening. But the idea of a theory is it can be sort of, I would say, revised. It can be found not correct in all aspects of it. So, for example, if you take something like we'll talk about, dare I say, chapter 4, I think, Dalton's atomic theory. Dalton's atomic theory talks about the atom and different parts of the atom. And one of the parts of Dalton's atomic theory is he said that all atoms of the same element are pretty much identical to each other. And that is actually incorrect because at the time they did not know about things which are known as isotopes. And isotopes are the same element, except that they have different numbers of neutrons, which means they're not identical to each other, even though they are the same element. So something like that is not correct, that part of his theory, but the other parts of his theory are actually still correct to this day. So theories are things that could be later proven not to be correct in all aspects, may not apply to every situation, or may turn out not to apply to every situation. Another example is something like Bohr's model or Bohr's theory of the hydrogen atom, which works really great for hydrogen that has one electron and anything else that has one electron. But if you try to apply it to things that have multiple electrons, it doesn't work so well. So again, that's the idea of a theory, which again can be revised, can be thought of as being correct at one point in time, and through further experimentation, found maybe not so correct in all aspects, not correct in some aspects of it, and things like that. Now, a law is something that no matter what the situation is, it's always going to happen that way. There's kind of like no exceptions. Like we could lock this in. This is always the way it's going to happen, no matter what the situation. For example, we could have the law of conservation of mass, which is one of the main reasons why we balance equations. So, for example, in a chemical reaction, if we started out with something that had, say, 4 carbons in it, carbon's about 12 grams per every carbon. When we're all done with that reaction on the product side and we make everything that was formed as a result of that chemical reaction, we will still have 4 carbons. They may just be in different things. But in terms of the mass of the carbon we started with, because we started with 4 and we ended with 4 carbons, we have a conservation of those elements, and we have a conservation of mass because we started with 4, we ended with 4. And again, why we really balance equations to make sure we have the same number of elements on each side. And that's because in a normal chemical reaction, which is pretty much what we talk about in this class, the only thing that happens is we just break everybody apart, all the elements, and they recombine to make new things. We never lose elements along the way. We never make new elements along the way in a normal chemical reaction. And that's why we do have conservation of mass. We also have conservation of energy, which means we do not create nor destroy energy. But we think of energy as being transferred in one form or the next. So if you think about energy, perhaps you've seen this example when they talk about energy and the classic potential energy, where you got the big giant boulder on top of the hill that's about ready to fall, down to the ground, and that boulder has a certain amount of potential energy based on its position. And as it starts to travel down, it will convert some of that potential energy into kinetic energy, which is the energy of motion. We don't lose the energy, it just gets transferred to somebody else basically along the way. Then when it splats there on the ground, hopefully nobody's underneath it, it will then also send out some energy to the ground and whoever's underneath it. But if you sort of add up all the energy, it just went somewhere. It was not lost. There was nothing created, just moved from one place to the next. And that's the idea of the law of conservation of energy. So we have these laws, which are, again, sort of locked in, always going to happen the same way. We have theories, which are really sort of how we think things are happening, models of how things are happening, but again, can be sort of revisited and may not be correct in every aspect. Any questions on that there? All right. So as I mentioned before, a lot of chapter 1 is about math skills. And again, there's no getting around it. There is math in this class. So this class really is broken up into three parts, or really two parts in terms of the math. The first part, which is all the chapters we do, I think 1 through 10, without chapter, I want to say 5 we don't do, maybe. But basically 1 through 10 is all the general chemistry, and that is all math, calculations, formulas, and stuff like that. So if math is good for you, then you'll probably enjoy those chapters. When we get to the organic and the carbohydrates, the biochemistry at the end, there's not a calculation to be found. You basically could put your calculator away. So when we get to like chapter 11 and on, it's all about memorization and that type of stuff. There's not one calculation I can think of that's going to happen. So this class kind of breaks into those two parts. So if math is not your thing, you just got to make sure you get through those first chapters. And then on the back end, you might have a better time because there's no calculations involved. Or if you really like calculations, you might like the front end and maybe not so much the memorization part of the back end. So it's kind of uh, two sort of classes in that sense. So again, we're not going to go over every single math thing here. I would recommend that you go over it if math is something that you have some trouble with. We don't do a lot of really difficult math here, but you definitely need to have basic skills in terms of how to rearrange equations, basic algebra to sort of solve for things. Those are the things that you do have to be able to do. We'll talk about ways you could kind of get around some of that in a sense, but that is what this part of it is. Identifying obviously what places in a number we're talking about. Obviously, to choose the thousandth place, hundredth place, tenth place, and ones place. We also have some decimal places. The tenth place is where the 4 is in this case. The hundreds and the thousands place along the way there. So obviously here we have our tens, ones, tenths, and hundreds place along the way. We have positive numbers and negative numbers that we deal with in here. So a couple of just basic math review stuff, right? If I add two positive numbers, I get a positive number, right? I add two negative numbers or subtract two negative numbers, however you want to do it, you get a negative number, right? If I multiply a positive times a negative number, right? I get what type of number? Negative number, right? I multiply a negative times a negative number. I guess put some parentheses around that. I get a positive number, right? So, plus there on the way. So obviously a couple of things in chemistry. Most of the time we don't write the plus part, obviously, if it's a positive answer. So we just put the number. But definitely if it's some type of negative number that you get, you should definitely put the negative and make sure that you do put that with your number when you do it. That's obviously what we just talked about there. Two positives give us a positive, two negatives give us a positive number as well. When we divide, same sort of rules, right? If we divide two positive numbers, we get a positive. We divide two negative numbers, we get a positive, right? We divide a negative and a positive number, we get a negative number, right? So again, those type of things. Addition, we just talked about there. Let's talk about our calculator and some of the important buttons. And really, I would say most people struggle with, as odd as it sounds, the calculator, yes, and how to properly punch things into your calculator. So they do have a lot of these sort of calculator operations here in the first chapter. So again, if you're not sure how to punch things into your calculator, besides asking me maybe how to do it, you could look through this chapter and it might help you with some of that. But let's just talk about some important things when we use a calculator. The very most common error that people make, for example, is if they have a bunch of numbers, and we'll just randomly throw up some numbers here. And then we want to divide by 43 times 12.22. So when people go to punch something like this into their calculator, very common mistakes are that they will try to punch it all in at once. And I would highly, highly, highly recommend you do not do that. So if you do that, you have to be really careful, depending on your calculator, to make sure you put parentheses around everything correctly. So my recommendation, for example, if you have something to type in like this, you take the top, basically, we're going to multiply everything on the top, and we're going to come back and divide by whatever's on the bottom, basically, in this particular case. I would highly recommend that you find this important button on your calculator, which is the equal sign. Yeah. People do not use the equal sign a lot, or the, enter, give me the answer sign. Mine's actually an enter button over here. So what you would want to do is, how you could properly punch this in and always get the right answer is, no matter how many numbers you have up on top, for example, you have as many numbers as you want. You can multiply all those numbers, as many as you got in a row. You don't have to put parentheses. You just take your calculator and go 425 times 32 times 12.45. When you get to the end, hit the equal sign or your enter sign, whatever is equivalent to equals on your button. Now, here's where people sometimes go wrong. They want to divide by what's on the bottom, and they put everything that's on the bottom in at once. What you should do is, by the way, you get some number like 169,320, I think, based on my calculator, is not change the page, but you should go back. And we're going to divide now, right? Anything that's on the bottom is going to get divided. So I would hit your divide button and divide by the very first number only, not both, just the first number. Divide by 43 and then hit your favorite button, which is equals. So divide by 43 equals. You get something like 3937.674419. Now you still need to divide by this number. Then you hit the divide button one more time and divide by that number, and then hit the equal button. So we'll divide by 122.32 and hit equals, and we'll end up with like 32.1915828, or actually 89 at the end there, I think, as well. So when you have multiple calculations you're going to do in a row, which happens a lot, especially in the first couple of chapters, very common people screw up with the calculator by trying just to put too much in there at once. If you were going to do this all at once, technically speaking, you got to lay up some parentheses, and make sure that you punch it in correctly. Most people do not do that. So if you want a way where you got something like that you need to get to an answer, and you're going to get the right answer, once again, if you have a fraction like that you got to get something on top and bottom, as many numbers as you want on top, no parentheses needed, just roll through them all, hit multiply, but hit that equals at the end of the top, and then divide by the first number, hit equals, divide by the second number, hit equals. If there's a third number on the bottom, divide by the third number, hit equals, and you will always get the right answer. And that's a very, very common error that people make as they try to use their calculator to do certain types of calculations. Again, they just kind of mess up that, just want to put everything in at once. So depending on how your calculator is programmed and may do the calculation correct, you might get lucky sometimes, but a lot of times you won't get lucky if you don't put the right sort of parentheses. Any questions on that there? Now, a really important thing, and obviously, like I said here, they give you some examples as to how to punch it into your calculator when you go through that sort of first chapter. Not do too much graphs. Let's talk a little about scientific notation here to finish up, since we kind of have the calculator and talk about the calculator. Scientific notation is something that's really important, and it has a general formula of n times 10 to the n. And this first number is a number between 1 and 10. So it is not 10, it's not 100, it's not 20. It's got to be less than 10 and not less than 1. So it needs to be, it can be 1, but it can't be less than 1. So it's got to be a number between 1 and 10. This is either a positive or negative number, and it depends on which way you need to move the decimal to get to a number between 1 and 10. We use scientific notation when we have really big numbers and really small numbers. When we have really large numbers or really small numbers, there's a very good chance there's a lot of zeros. which means if you're trying to write out all these zeros in your numbers and you're writing it down, there's a good chance you're going to miss a zero along the way and stuff like that. So if we had something like, 2640030, and we wanted to turn this into scientific notation, although there is not a decimal written, we do assume that it is about there at the end. And if we go one place, that is not a number between 1 and 10. We need to go another place. That is still not a number between 1 and 10 because that's like 26,000, right? So we got to keep going, keep going, keep going. That's 26.4, still not a number between 1 and 10. We do need to go one more spot. And that will give us a number between 1 and 10. That will give me a lot of numbers, 2.64003. I'll leave that 2 zeros off and I'll tell you why in another lecture. Times 10 to what did I count there? 1, 2, 3, 4, 5, 6, 7. I might have missed that for that wasn't a zero, was it? 1, 2, geez, where my decimal was. 1, 2, 3, 4, 5, 6 times 10 to the 6 here. And it is a positive because I moved the decimal place to the left in this case. And there is a reason why I dropped this last zero here. And again, we'll explain it in maybe in the next lecture. Now, if I had a small number like 0.00432, and I want to turn this into a number between 1 and 10, we're going to go one place. That's not going to do it. Two places, three places gives me 4.32, which is a number between 1 and 10 times 10 to the minus 3. I move the decimal place to the right. The exponent is a negative value. The easy way to remember that is if it is a number, kind of a large number greater than 1, it should have a positive exponent. If it's like less than 1, it should have a negative exponent, smaller sort of number. So we sometimes will put numbers into scientific notation because, again, they're really large or really small. We don't want to lose anything along the way. And if we need to go backwards as well, if we had something like 4.25 times 10 to the 3, what that tells me is this is a positive number, which means I actually need to move my decimal place to the right if I'm going backwards, because that's going to make it a big number, right? Because if I go to the right, that's like 42 now, right? As opposed to if I went to the left is 0.4, right? And becomes a smaller number. So we do want to go one place, two place, and three places. And we will have to add a zero in this case. Again, 1, 2, 3 places. And that will turn this into decimal form, if you will, sort of non-scientific notation. Again, there is a reason why there is not a decimal point written, which we'll talk about in the next chapter as to why the decimal point is not written in that case. First off, any questions on that? How this relates to your calculator is most everybody that I've ever met in my life does not know how to properly punch that into their calculator. So let's say, for example, you do have a number in scientific notation, like we'll go with 6.25 times 10 to the minus 6. Okay. So if you have a calculator, which you need for this class, it should have an actual exponent button, which will have a button that will say EE. It may have a button that says EXP. Or if you have some of the newer calculators, and these are usually kind of like the two-tone calculators, like it has a color in the middle and then the sides are different and stuff like that. It usually will have like a little wheel on it as well, towards the top right. That is your exponent button there. So we'll talk about what you need to do with this in a second. But if you have both of these buttons, these are really your exponent buttons and what you should use when you put a number in scientific notation into your calculator. There's also two other important buttons, which is your negative button, which oftentimes will look like this, or it will look like this. It is not your subtract button. So you should also have a negative button, for example. So when you put this into your calculator, you would hit 6.25, and then you would put your exponent button, either your EE button or EXP button. When you do that, your display should look something like this, 6.25 and an E. You may have 6.25 and it may pop up a couple of zeros. It may actually put a times 10 and a couple of zeros up on top. It'll look something like that on your display. When you hit the EE button or the EXP button, that stands for this part of the number, which means you do not need to hit the multiplication button. You do not need to hit anything like shift log or the log button or anything like that. All you have to do is put the rest of the exponent in. Now we have a negative exponent in this case, which means we do want to use our negative button here. So whichever one you have, you want to hit that. That will put a negative here. That will pop a negative up there on the display when you do that. And now we'll hit a 6. That will be a 6, and I will turn that into a 6. And that is the proper way to punch that number in scientific notation into your calculator. Again, at no point did I use the multiplication button to enter that number. I didn't use the log button, which is a common error people make, like shift log or second and log. That is the proper way. Question on that there. Now, if you happen to have a kind of that two-tone version with these two buttons, the only difference is your calculator is programmed terribly, let's put it that way, that you have to do a little extra work to tell your calculator how to do the math correctly. So if you do have the other buttons in the box here, you would have to start with a parenthesis and then put 6.25. You then would hit your times 10 to the n button. And on your display, you will have 6.25. It will actually probably put a times 10 on your display. You will now have a little blinking cursor box right about there on top. At this point, you could do the rest of it, which is you hit your negative button and 6, and it will turn that into 6.25 times 10 to the minus 6. Now you have your cursor button blinking next to the 6 up on top, which is a problem because if you try to close your parentheses at this point, you can get like a little small parentheses up on top, and your calculator is going to yell at you, you did something wrong. So that is where the little wheel comes into play. You then would need to take the wheel, you just press that side of the wheel. That will bring your cursor down to a normal size cursor where now you can close your parentheses and you will have your number now in scientific notation. I know it looks like a lot of steps when you get used to doing it. It goes really quick, obviously. But if you have a calculator that's sort of, again, a two-tone type calculator that has that little wheel and the times 10 button, you just got to put every single number in parentheses that's in scientific notation. If you have the EE button or EXP button, you don't have to be careful at all. You can just roll with the numbers and you don't have to do parentheses. They're programmed, I'll just say better, that you don't have to worry about that. You don't need to change out calculators if you have the other one. You just got to make sure you know how to properly do it. Right? Any questions on that there? All right, we will lay it up there.